So today we're going to be talking about tracing. Folks requested that we spend some time looking at the tracing code. Um, so let's talk a little bit about tracing from the context of, let's see, the logical, or the stages of the pipelines that we can trace, because there's sort of two parts to tracing. So tracing is effectively designed to memorize results of computations done in this pipeline, so that we can replay them much more efficiently than we did, maybe the first time we ran through the trace, right, and actually do the full analysis that we do, right. And so there's actually two stages here that you can actually trace. There's the logical dependence analysis stage that you can trace, and there's also the physical dependence analysis stage that you can trace and replay. And we're going to start with the logical one because it's sort of the one that came first, and it's the easiest to understand, and it's kind of required to understand how the physical analysis part works as well. But eventually we will probably in a later session get into how the physical analysis tracing works. We'll see how far we get today. Um, and let's see. So tracing is a little bit of a strange part to the Legion runtime because it kind of sits on the side to everything, right? It's not part of like the main part of the code. It's kind of like this recording mechanism that can record the results of logical analysis or the physical analysis and then play them back a little later. In many ways, it's like having like a little mini jitting compiler inside of your runtime system to capture some of these things and optimize traces and replay them. I will say today, one important thing about tracing today is that today we do require that applications and users tell us where the traces are, right? There's effectively a begin trace call and an end trace call, and you give a trace ID that uniquely identifies that trace, right? And that effectively is how we know that there's the same sequence of operations with the same region requirement arguments and stuff being passed in the same places, and therefore it's safe to do the replaying of the trace. And we do trust users to do that pretty well today. We actually need to put in some more checking code for that. One other caveat about the tracing code, as you're going to see today, is that the tracing code is part of some of the messiest code in Legion. It's kind of like, sort of evolved instead of really being designed. And as a result, like it really needs some cleanup and stuff, which we haven't had a chance to do really yet. But it's sort of evolved to handle the functionality that it needs to handle, but it certainly could use some cleaning up and some re-architecting. So take all this code with a grain of salt and realize that it might change, in the nearest future at some point as we refactor things. So we'll start today with logical analysis tracing, and if we get to it, we'll start doing the physical analysis tracing. But if not, we'll cover that in a later session. Okay. So let's take a look at how tracing starts. Let's see. No, this one. So let's actually go look at this begin trace call here. Right. So this is effectively where the user is telling us that they're going to start a trace inside of one of their contexts. So we're inside of our context object here, right? Like if you're in an inner context, you're going to be doing traces that are going to record, subsets of task launches and other stuff launched from this parent task. Right. And the user passes in a trace ID. You can say whether it's a logical only trace. There's also arguments for things like static traces and stuff. We probably won't talk about static traces. We'll assume that everything we're doing is dynamic tracing today, in which case this set of trees is going to be a null pointer. Don't need to worry about that. Deprecated version of this API and the provenance or where the trace came from. Right, and there's a whole bunch of like runtime arguments the user can use to like turn off tracing and stuff or turn off physical tracing. Right, so you can see some of our options here can affect, those parameters here, right? If the user has turned off tracing, right, there's a command line flag that you can disable tracing, so you can opt out of tracing, in which case this begin trace call just doesn't do anything, and so forth. So, the first thing that we do, inside of this begin trace call, right, is each of these inner contexts, has a set of traces that they're tracking, right? And so trace IDs are scoped, to the parent task that they're associated with, right? They're not global things, so you can reuse trace IDs across parent tasks or in like multiple copies of a parent task. You can, or different parent tasks, you can reuse the same trace ID and stuff like that. But each parent task sort of keeps track of all the traces that have occurred during its lifetime that it's seen, right? And it's stored in these logical trace, objects, which we'll go look at. But effectively, this inner context has got a set of traces, and so you look up the trace ID, right? And if you don't have one, right, it could be that you don't actually have the trace yet. Right, this is the first time you're actually going to be doing the recording, right? We'll make a new trace object for that and store it in in the set of traces and keep a reference on it and so forth. So you make sure you've got a trace, right? So that's pretty easy. The first time you see a trace, you need to make an object to record it. Otherwise, you've got it there for the rest of your run of your top level, or not your top level, but your parent task. And then really the next thing to do is really quite simple. You issue one of these trace begin operations, which is effectively going to be a mapping fence between the start, like all the operations that came before the trace, as well as all the operations that then come later inside of the trace, right? And the reason for that is effectively because in the case where you're doing a trace replay, right, the trace replay is only going to record like logical mapping dependencies between operations inside of that trace. It's not going to record any mapping dependencies between operations that came before the trace versus the ones that came after or came inside the trace, right? Because those might change from the trace capture to the trace replay, right? So what you do is you stick a mapping fence in between those two different, or in between the operations that came before the trace and the operations that came after trace. And just let me tie this trace begin up back to a mapping fence for you here. So we're in Legion trace.h here. If we go look at this trace begin op, you can see that's a kind of trace op. So trace ops are operations associated with tracing, right? So if we go look at that, right, you can see this is a kind of a fence op, and all fences are always at least mapping fences, and therefore effectively what you're getting here is a mapping fence between all the operations that came before the trace and all the operations that come inside the trace, regardless of whether you're doing a replay or not. Technically, we could probably align this in the case we're actually doing the capture only, but really it's not that expensive to put in when we're actually doing it. So we just simplify the logic a little bit so we don't actually put that in there. We just always issue this trace begin up to sort of demarcate the beginning of the trace today. There's another trace operation you can issue here for the physical tracing. We'll come back to this a little bit later. This is the trace replay op. This is one of those examples of something which should probably be refactored. There should really only be one operation here at the beginning of the trace, but we kind of have two of them right now because the physical replay analysis got glommed onto the back of the logical analysis. So these two things need to be combined at some point. But since we're talking just about the logical trace replay today, we'll just you just need this trace begin up. Sort of make sure that you're going to get any on a replay, you're going to get any mapping dependencies between things that came before the trace and things inside the trace, sort of implicitly handled for you that way. And notice that the context records.
Like, sorry, I have a question. Yeah. Just so my mental model of it is right, like the separation between logical and physical tracing, like I mean, in the SC18 paper, like
yep,
there doesn't seem to be a separation here. Like, are they presented as the same thing in that paper, or like, what is the?
I'm trying to remember how the 18 paper presents it. I actually think the 18 paper pretty much only talks about the physical tracing. I don't even think it mentions the logical tracing. Like, I'm not sure it makes that distinction. I think that
it just seems like there is an analysis that we have the results for.
And I think, the 18 paper, the 2018 paper focuses more on just the physical tracing, because that was the point of Wanchan's internship and stuff, and the system, the part of Legion that he built. And so I don't think it makes that distinction. But inside the runtime, there is definitely a distinction at the moment between these two things. Like there's a way to capture a trace that is logical only and only replay the mapping dependencies. Because that was the only way you could trace at the very beginning was there was only the logical tracing. And then Wanchan came along later and added the physical tracing stuff. But yeah, I think that paper is just the physical tracing. So realize that that's the case. Did I answer your question?
Yep.
Okay. All right, good. Okay. And the other thing that this context does is it records that it's got a current trace, right? So for all the operations that are going to come after this begin trace call, they'll be able to record that they're part of this trace that's going on, right? And that will either help them to either capture their mapping dependencies if it's the first time through the trace, or replay them if it's a later part of or if you're actually replaying the trace. right? And then we go off and we actually start, issuing operations just like normal, kicking off subtasks and other kinds of Legion operations that you can do inside of a trace, right? And then eventually you get to the end trace call, right? Which is, effectively the complementary call for into this context to tell us that we're finishing off this trace, right? And again, you get your trace ID and stuff like that. There's some error checking code here, right? Like you better have a current trace, right? Like if you did a double end trace call, that would be very bad, right? Legion would complain about that. Let's see. We do some checking to see if you did any like blocking API calls and stuff like that inside your trace. That's more for the physical tracing than the logical stuff. The logical tracing can actually handle blocking API calls, but the physical tracing cannot. And then there's effectively two different paths here, depending on whether this trace is quote unquote fixed. And this should really be renamed, but fixed is really a synonym for has this trace been captured or not, right? And are we replaying it or not, right? And so if you're already fixed, then what you're really doing is you're replaying, right? So you do this this trace complete op, right? And this is going to be another mapping fence, right? Another kind of mapping fence, right? To again capture mapping dependencies between things in the trace and things that come after it. Right, so that goes into operation pipeline to help out with that. And similarly, if you're not already fixed, this is the first time we're capturing this trace, so we do a trace capture op, which will effectively end up recording that this trace has been completely captured, and therefore it can then start to be replayed. And you see, this is the point where we fix the trace too, right? Effectively say that we've captured this trace, this logical dependence trace, right? And then we can set the current trace back to null. Right, and issue our operation into the pipeline, right? So it's useful just to keep in mind that like effectively every trace capture or end replay, for logical purposes, has a mapping fence before and after the trace, in order to guarantee that you get the right mapping dependencies hooked up, between operations on either side of the trace, because the trace is only going to replay mapping dependencies that are going to occur in between operations that are both inside of the or that are all inside of the trace, right? So that's something important to keep in mind. Okay, so that's effectively like how the begin and end trace stuff happens. Let's actually look at like how we actually capture mapping dependencies, as part of capturing this logical trace, and then we'll look at how it's being replayed. So the first thing to notice is we set this current trace. This current trace thing here, effectively, whenever we're inside of a trace, the current trace inside of a context is recorded as having, a pointer to this logical trace object. And that becomes important whenever you register a new operation with context. So let's see, actually it'll be in this file here. Register a new child operation, right? And you can see that, any registering a new child operation actually comes from, let's see, do I have the, yeah, here we go. From initialize operation, which happens on the base operation class, right? So, effectively, anytime you initialize an operation, as long as you're tracking the parent, which pretty much most things are, like, any kind of task or operation that you launch inside of a context, right? It'll call register your child operation. We've looked at some of this code before, so this should be kind of a reminder to everybody, right? It calls this register new child operation on the context, right? And the first thing we do is we check to see if there's a trace, right? And if there's a trace, we tell this operation, hey, you're part of a trace, right? And so, we sort of help fill that in. And when you do this set trace operation here, right, it'll actually, like, if we're replaying this trace, it'll actually fill in, or actually it'll record any of these static mapping dependencies and stuff like that. We're actually not going to record any or replay any mapping dependencies quite yet. We'll get to where that happens. But the other stuff that happens here, right? This gets recorded inside of the the window of outstanding child operations and stuff like that, right? And so this gets hooked into sort of the base, part of the pipeline for an operation starting to go through the pipeline with respect to its parent context. It gets told about its trace, and then every operation knows about which trace it's part of, if any, right? And an operation's trace could be null because that's the common case. There's not actually any tracing happening. Okay, so we've got, that's how operations, get associated with a trace as you kick them off. Let's actually take a look at how they record dependencies. So, like, recall that, like, as you're running through your region tree analysis, right? We've looked at the logical analysis before, and we looked at this, what's it called? Register logical user, yep. Actually, I want this version of it. Let's see. Here we go. Right, so we call this, we've looked at this method before, this perform dependence analysis method. This is sort of the entry point, for performing dependence analysis for a region requirement inside of a, for any kind of operation, right? So anytime you want to do logical analysis, for a given region requirement for an operation, you call this method, right? And then it goes through the region tree and looks for mapping dependencies and stuff on prior operations that use those regions and stuff like that, right? And the important method usually when you go through this, right, is, and you'll have to go back and look at the logical analysis if you've forgotten this part, but I'll refresh everyone's memory, right? This will go through the region tree, compute mapping dependencies, and eventually you get to this, let's see, where is Legion Ops again? I've lost it. You get to this like register region dependence, or you either get to this register dependence API call or register region dependence, right? And these are the things that will actually record mapping dependencies on prior operations inside of your parent task, right? And you get passed in your region requirement index, the target operation that you want to record your dependence on, the target region requirement index, and stuff like that, right? And the kind of dependence and so forth. And this is the important part where where there's actually some hooks in here for tracing, right? You can actually see it here. You can also see it here, right? And what this does is effectively, if you're recording a mapping dependence of any kind between these two operations, and you're part of a trace, like this operation is part of a trace, right? It'll actually go and tell the trace about the mapping dependence that's being recorded, right? In both cases, it'll go and tell the trace, hey, here's the mapping dependence that occurred between two operations, right? Now, the interesting thing is these operations might not be entirely inside the trace. All that we're guaranteeing is that one of the operations, the source one, is actually inside of the trace, right? And I say source here, I mean the one that's going to depend on a prior operation, right? So these targets are like sort of prior operations in the program order of execution, right? And so, but these things might not be outside of the trace, and so tracelet is going to have to check to see whether the mapping dependence that we're recording here has both of these operations inside of the trace. But we effectively do this call.
Yeah. By putting the fence, but we put a fence at the beginning of the trace though, right? So shouldn't we why are we still seeing things outside of the trace though?
Well, because we're computing. This is the recording part, right? So we're doing the recording, right? Like a mapping dependence doesn't like a mapping fence doesn't go prune prior operations out of like the region tree data structures, right? Like the region tree data structures still have references to prior operations that were computed or we're using particular regions and stuff like that. And so as you're doing the recording, right, you're still going to be computing dependencies on operations, that are in the region trees, right? And some of those mapping dependencies might exist between operations in the same trace, and some of them might, depend on operations that came before the trace started. Does that make sense?
I think so. So I mean, there will be the mapping, there'll be the fence already. So that's like one of the dependencies we might see. But then prior stuff before we'll also get as well.
Right.
We don't get the transitive dependence.
Yeah, the mapping fence. Effectively, this is the mapping fence during the recording process. Like let's keep two things straight. We're talking about recording here versus replay, right? Technically, the mapping fence is really only required during the replay part. Right, like let's imagine that code was like the begin trace call was actually a little more sophisticated and only issued the mapping fence, right, at the point where we're actually replaying a trace versus recording it, right? Like, so let's imagine we don't have the mapping fence at all during the recording process because really we don't need it, right? So during the recording process, we're still analyzing all of our region requirements and features and stuff to see what dependencies they have on prior operations, for mapping dependencies, regardless of the fact that we're capturing a trace, right? We're doing the normal logical analysis as if like nothing was different during the recording process, right? And so, all that's happening here is like during this, that process of computing those mapping dependencies, we're now going to tell the trace about any mapping dependencies that we're observing. And the trace, effectively is going to have to do the recording of the mapping dependencies between operations that are all inside of the trace. But you might also get, calls here where we're told about mapping dependencies between operations that are inside the trace and operations that came before the trace, right? And so We tell the trace about all of those things, but the trace is going to have to figure out which ones are actually still, are the ones it needs to actually record. Did I do a good job explaining that, or more questions?
Yeah, it makes sense to me.
Yeah. Right. So the trace gets told about, all these kinds of mapping dependencies, like pretty much every kind of mapping dependency you might record, during the process of analyzing any operations inside the trace. The trace object is going to get told about those things. So if we actually go look at Legion trace dot here, so what did I call it? Record dependence. There we go. If I can spell correctly. So there's record dependence, and there's also record region dependence. One that has some information about region requirements, and one that's just sort of the generic one. I will take a look at this one first because it's actually a little bit simpler. But the first thing that we actually do, right, is effectively inside of the trace when we're recording a trace. Every one of these logical traces, effectively keeps a mapping of, let's actually take a look at this trace data structure, and then some of these things will make a little more sense. So actually go look at logical trace here. Right, so effectively this is going to be our object that's going to sort of represent the trace and capture all the logical dependencies that exist inside of this trace. And to do that, has a couple of data structures, right? So every trace object is associated with a context, has a trace ID, it's got some provenance. Let's see. It's got a pointer to its physical trace, which is something we'll look at a little bit later. It's got some state that we'll track here, like fixed is recording whether or not we've captured this trace or whether it's the first time through. The most important things, though, are the things down here. This is actually probably the most important data structure here, this operations vector. What this is effectively a vector of operations and their generation IDs, right? Effectively, because operations can be recycled, so you need a generation ID to make it unique, right? But these are the set of operations that got kicked off, for actually either recording or replaying this trace, right? And so it's a way of, recording the set of operations. Let's see. And then, for each one of these operations, there's a set of operation infos, which is going to record all the mapping dependencies for each one of these operations, right? So this effectively is the trace. And as you're either capturing or replaying, this vector gets populated to record, the operations in this particular iteration of the trace. And then for each one of those, you can sort of like look up the thing at the same index. And this operation info will record all the mapping dependencies on other operations inside of the trace, right? This operation info is actually defined, up here, right? And you can see that it's got, effectively a set of dependence records, right? These are mapping dependencies on other things inside the traces, inside of this trace, as well as like some information about close operations that have to be issued and stuff. And it's also got some primitive, things for doing checking, like what kind of operation should this be, and what does the region requirement check count. Those are ways of, verifying that that application is abiding by the rules of tracing, that it's launching the same kinds of operations, the same regions in each order. Really, this needs to be much more robust, but these are sort of like primitive checks that we've got right now. But effectively, this is the trace right here, this replay info. And then, on either a capture or a replay, you've got this like list of operations that were launched inside of this particular trace. And you see this data structure here that's going to come up real shortly here. We've got this operation map, which is sort of a way of associating a unique operation with a particular index in this vector or in this replay info, associated with the order in which operations were launched inside of this trace. You can look up things that were inside of this particular trace, and you only need this during the trace capture part, as the comment says here. So let's go back and look at this function here. It'll make a little bit more sense now. Right, so if we're going to record a dependence, the first thing we do is check to see if the target operation that we're trying to record this mapping dependence on actually exists inside of this trace. Right, so effectively we make our unique key for it, right? Effectively it's operation generation ID pair, right, which are arguments here from the actual API call, right? And then we do the lookup, right, and check to see if it's inside of our backwards mapping of operations. And if it's not, what that means is that this target operation actually came before the trace started, right? And so we don't actually need to record any dependencies on that. That's not our responsibility. That's an operation that existed before the trace began, right? And so we don't have to do anything, right? Otherwise, if it is, then we should be able to look ourselves up, right? And it better be there. There's actually an assertion here to that extent, effectively saying, we better be inside the trace if we're getting the API call here for this particular operation, the source operation, right? And so at this point we've got both of our two operations, and we actually go and record things. Let's see. Just checking here. What this particular thing is saying here. Effectively, if there are dependencies, between two operations in the same at the same point in the trace, right, we can actually ignore that. That occurs in cases with refinement ops and stuff. So you can actually ignore that. That's a very special case for effectively ignoring refinement operations, which are used for picking equivalent sets and stuff. If those happen during a trace capture, we don't need to record those because they're not going to be necessary during the trace replay. So we don't replay refinement operations and stuff. So this is just a special case to elide that. And now the next thing we do is effectively we want to update the operation info for our particular operation that we're going through in the trace, right? Now, effectively, this replay info, right, is actually it's always the last thing, because we do logical analysis in program order, right? It's always the last operation info in this vector or deck, right? Just refreshing everybody's memory. This deck right here, right? Effectively, there's like every time we add a new operation to the trace, we bump the size of this deck by 1, right, during the recording process. And so always the last one is always going to be the one that we're going to be recording into because, operations go through logical dependence analysis in program order. Right, so we get the operation info, and then our goal here is to actually do a dependence, add a dependence record to this particular operation info. So dependence record is effectively just a mapping dependence. It's actually just defined up here in this inside this logical trace operation here. Here's a dependence record object, right? And effectively it tracks our operation index, the previous operation region requirement, our operation region requirement, whether or not it does validation for resilience and stuff, the kind of dependence, and which fields it was associated with. Right, and each operation info has a vector of these dependence records associated with all the mapping dependencies for this particular operation. So we're just adding to this this vector here. Right. Let's see. So I'm just looking at the two cases here. There's a special case here for if we're recording a merge close operation. Right. In that case, we actually want to record that the prior operation needs to do a close operation. I'm not going to go into too much detail for that, but effectively. If it's not the more common case is this one down here where you're not doing any sort of special stuff with close operations and fences and things like that. In which case we go through the set of existing dependencies and then we try to merge in this dependence record, right? And the idea is that we try to collapse dependence records wherever possible to record as few as necessary in order to minimize the amount of mapping dependencies we actually have to replay. So we do a little bit of merging of those. If you can share a dependence record between two things, we'll actually do that so that you can sort of do that. And if you haven't recorded it, then at the end we just stick it into the back of the vector, right? And say that we've recorded that new dependence record. And something similar happens with the recording region dependencies. A lot of this code looks very similar to the one above, with some exceptions for special cases for merge close ups and stuff like that. But this code is very similar to the one before. Except for the dependence record is a little bit more robust, records a lot more things about what's actually happening and stuff like that. So at the end result of this trace capture, what you get is effectively a fully populated set of these replay info operations, right? And what happens then is when you go to start replaying the trace, the next time you come through and you start to replay this particular trace. Right, the next thing that will happen is actually that, let's see if I can remind myself where. So let's see. If we look at set trace, I think that just sets the actual. Where did lead jobs go? So let's take a look at what happens. Yes. So let's see. So this is the case where if we're doing a replay, right, if we're not recording, we've already recorded the trace and we're trying to do replay, you set this trace operation, right, and you call trace initialize op tracing. Let's take a look at where that goes. Oh, yep. Okay, that doesn't do anything. Okay, yes. Oh, I'm in the wrong class. So dynamic trace is actually where we want to be. Right, so register operation is where I actually populate the dependencies when we actually do the replay. Let me see if I can remind myself how register operation gets called here. That's not the right. There we go. Okay, yes, this is how it happens. Okay, so I told you before, like, I actually should probably have shown you this as part of the trace capture, but this is true for both trace capture and trace replay, right? Effectively, at the beginning of the logical dependence analysis, right, this is the begin dependence analysis call on a base on the base operation class. So for all operations, of any kind, anytime that they go through, the dependence analysis stage of the pipeline, and they've got a trace, right? They get this trace register operation call, right? Before they do any physical analysis, right? Any logical analysis, right? This begin dependence analysis call happens before the trigger dependence analysis stage of the pipeline for any kind of operation. So this register every trace will register a new operation before it begins doing its logical dependence analysis, stage of the pipeline. Right, and so every trace will get registered a new operation. And if we actually go look at this register operation call, right, effectively there are two parts. Again, there's the capture and the replay part to this, right? First off, we should be tracing here, right? In fact, like this if block is probably almost redundant, I think. Yeah, we should be tracing in this particular case, right? Let's see. So, let's see. I'm just trying to look at this. Look at what happens here. Oh, yeah. Okay, I'm remembering this now. So this is the case where we're actually doing the capture here, and then this is the replay path down here. So right in the capture place, right? I told you that we appended to this vector of operations, and we added something to the list of dependencies, and we record this op info for this particular operation, right? Like these are effectively all the initializations that I sort of for these data structures that we looked at back here, right? So every time you add a new operation to the trace, it adds a new thing into this operations vector. If we're recording, it adds a new thing onto this replay info, records ourselves in the operation map for and stuff like that, right? That's what's happening in all of these statements here, right? Otherwise, this is the internal path. We don't need to worry. I'm not going to talk about how we record the map merge fences and stuff today. It's a little bit too much detail, but effectively, it's a part of this. And then this is the replay path down here, right? So effectively, this is the path where we're actually going to go and replay this. We're replaying this trace, and so what we want to do is actually replay the logical dependency analyses that we computed, in the prior path, right? We'll talk a little bit about these frontiers here in just a minute, but for now, just ignore this part. There's some very primitive checks here for tracing violations, like did you issue different kind of operations, or did you issue more operations than there are in the trace? That's a violation, right? If the operation kinds don't match, if the operation region requirements don't match, those are all violations. Really, we need to do a much more robust thing here and actually check hashes of all the region requirement arguments and stuff to make sure that the tracing condition isn't being violated. That's a to-do to make this these checks a little bit more robust. But we've got some primitive ones in here just to make sure you're not doing anything really dumb. Let's see. If we get down here, we're in a good place now, and our goal is to actually go and replay all of the mapping dependencies, right? And so effectively we do add ourselves to list of operations, and then we can actually go look at our operation dependencies, right, at our index in this trace replay, so we can get our vector of dependence records. And then what we do is we just iterate over all those things, right, and record dependencies on the operations that came before us in the trace, right? And that will effectively re-compute, re-add in those mapping dependencies without having to do any logical analysis, right, like traversing the region tree and stuff like that to figure out where the dependencies exist on prior things inside of the trace. And if there were dependencies on things outside the trace that came before it, right, those all get handled by that mapping fence that we looked at, in that begin trace operation ahead of time. Right, and so this is really just replaying these mapping dependencies. You can see it actually calls back into things like operation register dependence or operation register region dependence, right? And does those API calls to to add in the mapping dependencies, just like you would have done if you had actually run the region tree analysis for logical dependence analysis, right? Let's see, and I think this is the path down here for internal operations. Yes, so effectively this is the path for how you do replays of internal operations and stuff that are recorded. So I'm not going to talk about that here, but effectively these are all like this is how we actually replay, right? So effectively right at the beginning of the dependence analysis, we will go through and replay all these mapping dependencies right at register operation. And then, just to close the loop here, right? Because like trigger dependence analysis will still get, where'd it go? Right, so we still do this so effectively after this API call here and begin dependence analysis, all the mapping dependencies are actually already added to this particular operation. Now, each operation will still get its trigger dependence analysis API call, right, to actually do its dependence analyses, right? But effectively, there's a fast path out to determine whether or not you actually need to do that dependence analysis. So I'll show you this little thing right here. This is actually in the region tree analysis here, right? We got this logical trace info object, right, which helps with recording stuff during trace analysis. But the first thing you do is you actually check to see whether we can skip the logical analysis, right? So effectively, if we're replaying a trace, you can actually skip all the rest of this perform dependence analysis on every region requirement in your operation. And that skip analysis gets filled in by this logical trace info. Let me actually show you where that happens. That'll be in legionanalysis.cc. Where is logical trace info? Right, you can see the skip analysis here. Right, effectively we better have a trace, right? And we ask the trace whether we can skip the analysis for it. If we go back to Legion trace, look for skip analysis. Right, effectively, as long as we're not recording, right, we're able to skip the logical analysis for performing region tree, for traversing the region trees and stuff like that. So that's how you quickly opt out of doing the logical dependence analysis for every region requirement. It's worth noting that this wasn't the way that logical tracing used to work. In fact, like when the 2018 paper for tracing was written, logical tracing analysis and replays actually still had to do the traversals of the region trees for esoteric reasons that we probably won't get into today. But that actually led to some unfortunate decisions in how physical tracing ended up doing, because logical tracing replay was much more expensive than it is now. And so effectively there's some, as we get into physical replay or physical tracing, and we'll actually see that there's some unusual decisions that were made because of how expensive the logical trace replay used to be. But it's not that way anymore, and therefore, some stuff needs to change in the physical tracing replay to reflect the fact that it could probably be done a lot simpler now than it is, because the logical tracing replay is actually much more efficient today than it is before, because it skips the full region tree analysis that it used to have to still do for replay before. Let's see. Oh, so I did mention that I wanted to come back to that concept of the frontiers. Where did Legion Trace go? So let's go back to register operation. Here it is. Let's see. Is the right one? Yes, I think so. Oh, yes. So here's our set of frontiers. And let's actually, I need to remind myself exactly, right? So the frontiers are effectively so the frontiers are effectively, the things that effectively are the operations. Okay, so let me explain. Yeah, all right. Let me start again. What the frontiers are and what the motivation is for it. Let's actually go back and look at Legion context again. Where'd it go? Did I lose Legion context? Here we go. Right, so recall at this end trace operation. Is this the right end? No, not end task, but end trace. There we go. And probably not the control applicator version. There we go. Right, so recall that at the end of end of trace, we actually do this trace capture operation, right? Which effectively is going to have to be like a mapping fence at the actually, really the interesting one is this trace replay, or sorry, trace complete operation, because it's the one that occurs at the end of our logical analysis trace, right? Effectively, if we're doing a replay of a logical trace, right, we need to have a mapping fence at the end that records dependency on all the operation, a mapping fence that records mapping dependencies on all the operations in the trace, right, such that anything that comes after the trace will actually get mapping dependencies on anything inside the trace, right? Because like the things inside of the trace didn't actually record logical dependence analyses, in the region trees and stuff like that. So the only way to get a mapping dependence on things in a replay is effectively get it through this through the mapping fence associated with this trace complete op, right? But this trace complete op, right, effectively, if you've got a really big trace, one way you could implement the mapping fence for this trace complete op is it could just go through like all of the operations inside of this, list of operations here and try to record mapping dependencies on all of them, right? And that's a perfectly correct and sound way to implement, the fence at the end of the trace replay, right? But that would actually be really expensive for very large traces, right? You might have like hundreds or even thousands of operations inside of this vector, right? It's not uncommon to have traces that are very large that way, right? And so you don't want to have to go through those and record mapping dependencies for your fence on every single one of those. That would be time consuming and very, very painful to actually do, right? And so what we do is we keep track of this set of frontiers, right? And what the list of frontiers is, you're going to see this concept come up in the physical tracing too, but the idea is effectively you keep track of all the operations that are inside of this trace so far that effectively have that have recorded mapping dependencies on other things inside the trace, but haven't recorded dependencies, haven't had anything downstream from them inside the trace recorded mapping dependence on them, right? So effectively, these are the operations which which do not have any mapping dependencies recorded on them yet inside of the trace. And when you get to the end of the trace, right, then the mapping fence at the end only needs to record mapping dependencies on these things on the frontiers, on the frontier, right? The frontier is the set of things which haven't had any prior operations record dependencies on them yet, right? And then that'll transitively get you dependencies on everything inside of the trace, right? So this frontiers data structure, right, we actually keep track of it here, right? Effectively, it's we add anytime you add a new operation to trace, it immediately goes into the frontiers. And then when you record dependencies on things, you can actually go and remove them from the from this frontiers data structure. So let me actually go back up. Let's see. Where did that? Yeah, I should have actually been in this method here, I think. Yeah. Right. So effectively, when you actually are recording a dependence, right, you actually look for the set of frontiers on the target, and if you can find it, you then remove it, right? So effectively, anytime you record dependence on something, that removes it from the frontiers, right? But things go into the frontiers as soon as they're first added, right? And so when you get to the end of the trace replay, right, all you've got left are the operations which haven't had any mapping dependencies recorded on them yet, and therefore your mapping fence needs to record dependencies on those to capture effectively a transitive dependence on every single operation inside of this trace replay. And the trace begin op, or sorry, trace complete op, right, effectively can then go through and just use that frontiers data structure to record mapping dependencies on that to capture the transitive dependencies. So, and actually, let's see if we can actually find that. Let's look at trace complete op. I'm doing this one on the fly. Haven't looked at this one recently, but pretty sure it should be there. Yep. There's lots of stuff in here for, I think we want this trace end execution right here is the important thing. And this is in the logical dependence analysis stage. Notice we're in trigger dependence analysis for this trace complete op, right? And so if we actually go look at end trace execution on a logical analysis, or on a logical trace here, right? This is the not recording path, right? And you can see we're iterating over the set of frontiers here, right? And recording mapping dependencies on all the things inside of the frontiers, right? And that's effectively how that trace complete op can then, go through and record mapping dependencies on, all the things, transitively record mapping dependencies on all the things inside of the trace without needing to, record a dependence on every single operation that was recorded as part of the trace. Okay. So let's see. I think that's the important parts of logical tracing. It captures the general concepts. I think the main thing to take away is that effectively the nice thing about logical tracing is that the first time you do the trace, you do the capture. All the later times, you do replays of those mapping dependencies. Things are going to get a little bit more complicated with physical tracing, where it's not always obvious whether you're recording or replaying, because it depends a lot on mapping decisions and where data is and stuff like that. But logical dependence analysis is invariant to the mapping decisions. So that part is the same regardless of the first time you see the trace, you do the recording. All later times you see the trace, you do replays. That's very simple. Um, uh, let's see. At this point, I think I'm going to stop and open up for questions. I don't think we're going to have enough time to get started with physical tracing today. But we can do that part the next time. So any questions I can answer.
So I'm wondering how how important doing logical tracing is like for the overall runtime of the program. Because I mean, my mental model of this was that physical tracing is sort of, I mean, physical analysis is always much more expensive than logical analysis, right? So I guess you said historically we started off with just logical tracing, right?
Yeah.
So and what's the story there?
Yeah. So well, it actually it didn't used to be the case. Logical analysis used to be almost as expensive as physical analysis in much older versions of Legion, which is why like the first version of tracing just did logical tracing. The other important thing about logical tracing versus physical is that like even though it's cheaper now to do logical analysis versus physical analysis, logical analysis is still sequential, whereas physical analysis can be parallelized if there's actually task parallelism between region requirements and stuff like that, right? And so we really do still want to get it off the critical path. Like we want logical analysis to be as fast as possible to push things through the pipeline quickly, right? Because you can't parallelize logical analysis. Like operations have to go through the logical dependence analysis stage in program order. So there's still value in tracing and replaying it. It's certainly much cheaper now than it used to be. So it doesn't make as big a difference, but the idea is still to you still want to reduce as much overhead as you can, and so it helps to get that logical analysis out of that sequential bottleneck.
Makes sense.
Yep. And yeah, so and right now actually like we're still like running operations. So I'll preface this part to the physical analysis. So it used to be just the case that well actually let's see. Yeah, it used to be the case that the physical tracing would sometimes effectively try to preempt the logical tracing too, because it used to be so expensive. Where the physical tracing would effectively say if we're going to do a physical trace replay, ignore the logical tracing replay because it's so expensive, and replay the physical tracing in the logical dependence analysis stage of the pipeline. And that has caused more bugs and problems than I can count. And we're in the process of refactoring things to remove that because the logical tracing is now much cheaper than it used to be. And it actually does a very, very good job at replaying quickly. So and that will clean up a lot of the code that we're going to see in the physical tracing the next time. But yeah. Any more questions?
Yeah, I have one question about the relation I think now between logical and physical tracing.
Yeah.
So
Okay.
Once you have a physical trace, like why do you I guess why I mean it's like why do you need to have the logical trace at all?
Well,
Because the physical trace captures all the actual dependencies.
well,
Right?
so this was one of the things we'll look at next time, but there is no such thing as one physical trace, right? Like you can have an arbitrary number of physical traces because physical traces depend on the preconditions, and the mapping decisions made during, the process of recording the physical trace, right? So you can actually have multiple templates for a physical trace, which correspond to like different preconditions, associated with that trace and different mapping decisions that are made during it, right? Like you could have, the same trace ID, right, from the application's perspective, but maybe like one time like the input data exists on the CPU, right? And so you captured a trace, which we're going to end up calling a template, right, associated with replaying, on the CPU, and then another one where the input data, for the trace exists on the GPU, and you capture a different trace or a different template associated with, replaying on the GPU, right? And you can actually have an arbitrary number of templates for every physical trace associated with different preconditions and different mapping decisions and stuff like that. And so just because you've captured one template doesn't mean that you're going to guarantee to always replay that template. You could actually have like multiple different templates that get replayed under different preconditions, right, for a physical trace, right? And as a result, like you may need to redo mapping the logical dependence analysis stage of the pipeline because you're going to need to recapture a new template in the middle of your run, even though you've already previously captured other templates for the physical trace. So does that make sense, or?
Yeah, yeah. I don't know. It seems like terminology-wise, you might consider the different templates of a physical trace to be like different traces, right? Like I don't know.
You can think about them that way, but
suppose if you treated them as different traces, then you wouldn't need to also have logical analysis involved.
But the application can't tell us that there are different traces, right? Like the application can only think about trace IDs in terms of operations and region requirements launched, right? Right, like the trace ID is associated with it's not reasonable to ask the application to use different trace IDs if it's going to make different mapping dependencies or mapping decisions, right? Like that's the mapper's purview, right? So the application can only assign trace IDs based on the order of tasks and operations and the region requirements and stuff like that.
Mm-hmm. Oh, I guess right. The application just issues the begin trace, and the mapper can deny the trace request and make a different choice, right?
Yes.
Okay.
Yep. Or the preconditions, like for replaying the previously captured physical traces, could just be different, right? Because like you could have like a begin trace, end trace, right? And then for the operations between the end trace and the next time you come around to the begin trace, they could have changed their mapping decisions, and then the preconditions won't match to the physical trace replay, and you'll have to capture a new one, right?
Yeah, I think that makes sense. If the logical dependence analysis replay is already cheap anyway, you might as well,
right?
Yeah, just have it.
Yeah, because it's not guaranteed once you've captured a physical trace that you'll always be able to replay the same thing, right? The preconditions to that physical trace could change, right? And therefore, you might not be able to replay it. There's also another case where I think that physical traces should change in the future, which is like they should. Today, we're going to see this next time, but physical traces today kind of like lock down their physical instances, and prevent them from ever being garbage collected, which can cause you to run out of memory in some cases. And I actually think that traces should actually be required to relinquish their dependencies, or not dependencies, the references on physical instances, and then reacquire them at the beginning of the trace replay, right? And that way you don't get out of memory conditions where traces, you've got like multiple templates that are all holding references that prevent collection to physical instances, which we have today, which is really unfortunate. And so like in that case, a trace might be a template might be invalidated because like some of the instances associated with it got collected, right? And then the trace is no longer, the template is no longer valid, right? So like there should be lots of reasons that you might need to recapture a template in the physical tracing. And therefore you want to replay the logical dependence analysis for those things. Okay, well, I promise to some of this will become more clear next time we actually start talking about the physical tracing side of things. Okay, any last questions? Last chance. Alrighty, we will start physical tracing next time. See you guys next week.